One appealing synthetic strategy for building long hydrocarbon chains with relatively complex structures involves first running a sequence of reactions to substitute an alkyne with another R group, for example by treating with strong base to deprotonate the terminal alkyne and then hitting with an alkyl halide to do a substitution reaction, and then reducing the alkyne to an alkane through some kind of hydrogenation reaction. The alkane product contains 4 new hydrogens relative to the alkyne starting material, and so we would need to add, for example, 2 equivalents of H2 to accomplish this. In fact, we can do this readily using a palladium or platinum catalyst, the exact same hydrogenation reaction that we've seen previously for alkenes. However, if we want to stop at the alkene stage, we need to actually apply a different set of reaction conditions, as the palladium or platinum catalyst on its own is so active that it's going to convert the alkyne right to the alkane in an uncontrollable manner. If we want cis or trans alkenes out of this reduction, we need to apply different strategies. In this video and the next, we're going to look at these strategies for syn addition of H2, leading to a cis alkene, and trans addition of H2, leading to a trans alkene. The strategy to obtain the cis alkene product via syn addition of hydrogen uses the fact that this reaction, treatment with hydrogen gas and a palladium or platinum catalyst, is itself syn addition of H2. If we can somehow change the catalyst so that it reacts very slowly or not at all with alkenes, but reacts relatively rapidly or rapidly enough with alkynes, then we can stop the reaction at the cis alkene stage. And the magic reagent here is called the Lindlar catalyst. It's actually a palladium catalyst that's been poisoned with some other components, specifically calcium carbonate and lead, and it's really the introduction of lead that poisons the catalyst and makes it much less active in hydrogenations of alkenes. Using this catalyst, we can stop hydrogenation at the cis alkene stage and isolate the cis alkene product. When an alkyne is treated with H2 gas and a palladium on carbon catalyst, hydrogenation occurs to go all the way to an alkane product. This reaction occurs through a cis alkene intermediate, in which only 2 hydrogens have been added to the alkyne. As this product is generated, however, it's rapidly consumed through a second hydrogenation event, leading to an alkane product in which 4 new hydrogens have been incorporated. And so this reaction involves 2 sequential syn additions of H2 and occurs via a cis alkene intermediate. As we just mentioned, we can use this hydrogenation as part of a synthetic strategy for building long hydrocarbon chains. Let's look at a quick example to see how this works. Say I started, for instance, with 1 pentyne, and I wanted to synthesize a hydrocarbon product with 7 carbons, heptane. In order to do this, I would somehow need to substitute this carbon, which now bears a hydrogen and corresponds to this carbon, with this ethyl group on the right-hand side of the heptane molecule. In addition, we'd have to somehow reduce this triple bond down to a single bond, adding hydrogens to the carbon highlighted in blue and the other carbon of the alkyne highlighted in green to convert the alkyne to an alkane. And hydrogenation can fulfill this latter need, this reduction of the alkyne functional group to an alkane. To accomplish this synthesis, then, we would first treat the alkyne with a strong base, strong enough to deprotonate the terminal alkynes, something like NaNH2 or NaH, and then we would treat with an alkyl halide that allows us to install this ethyl group. Ethyl bromide, ethyl iodide, any ethyl electrophile, the ethyl group connected to a good leaving group. The resulting product contains a new carbon-carbon bond, and the right number of carbons to generate the heptane product. However, it still contains the carbon-carbon triple bond. To convert this alkane into the desired product, heptane, we can then take advantage of hydrogenation, using H2 and palladium on carbon to fully reduce the triple bond to a single bond. What if we wanted to halt the reaction at the cis alkene stage? Well, since we know that the cis alkene is an intermediate of hydrogenation, we can use similar reaction conditions using H2 as the hydrogenation reagent with a catalyst that's not as active. And the magic elixir here is what's known as the Lindlar catalyst, palladium and lead on calcium carbonate. This reagent is much less reactive with the cis alkene intermediate after 1 hydrogenation than simply palladium on carbon or platinum. And that means that we can isolate this cis alkene without worrying about over-reduction to an alkane product. Because the product of Lindlar hydrogenation is an alkene, this provides an entry into all of the alkene addition reactions that we've already seen. And what this enables is the synthesis of specific diastereomers of substituted alkane products from alkynes. Let me show you what I mean by that. Let's say we started with this symmetrical alkyne containing two R groups. Partial reduction of this to the cis alkene using the Lindlar catalyst, palladium, calcium carbonate, and lead, yields in a stereospecific way, that is, only the cis isomer forms an alkene product. We can then use any of the stereospecific addition reactions to alkenes to generate a specific diastereomer of product. For example, treatment of this alkene with Cl2 leads to a specific diastereomer of product derived from anti-addition of the chlorines across the alkene pi bond. If you're having trouble seeing that this is anti-addition, notice that we started with a cis alkene, and the way the backbone is drawn in the product indicates a trans-looking relationship between the R groups. Of course, if we had a way to generate the trans-alkene product from the starting alkyne rather than the cis, the same reaction, through the exact same mechanism, would lead to the other diastereomer of product. In the next video, we'll learn a method for generating transalkenes from alkynes, using reaction conditions that are radically different from the hydrogenation conditions we've looked at so far. The point I want to make for now is that it's these hydrogenation reactions that really set the stereochemistry leading to these two diastereomers. The fact that the trans and cis alkene products of these hydrogenation reactions are themselves diastereomers, and the fact that the subsequent alkene addition reactions are stereospecific, means that the production of a specific diastereomer in one of these partial hydrogenation reactions leads directly to a specific diastereomer of the addition product.